Hi, everyone. Welcome back to the final section of this algebra course, the final section of this chapter. We're going to wrap up the course by talking about rational functions. So normally you would think that talking about like real and complex zeros of a function is like the perfect way to end an algebra course. But we got to tack on one more section since it's the end of chapter 3. So um, yeah, we'll get right into it. Some similar stuff, some new stuff, but nothing here that's really going to blow anybody's mind, I don't think. So, rational numbers are numbers of the form p over q, where q doesn't equal 0. So, rational functions are functions of the form p of x over q of x, where q of x does not equal 0. P of x and q of x are themselves polynomials. So as a reminder, no radicals, no absolute values, no rational exponents, right? Just straight x's to whole number powers. The domain of rational functions are all the places where the denominator does not equal 0. But you know what? We talked about that in 2.4 plenty of times. But just as a reminder, 1 over x minus 3, we want to make sure the denominator does not equal 0. So in this case, add 3 to both sides. So x can be anything to the left of 3, everything to the right of 3, just not 3 itself. The domain of x plus 1 over 4x minus 8. So denominator can't equal 0. Add 8 to both sides, divide by 4, and x can be everything to the left of 2 with everything to the right of 2. Okay, then here we go. X minus 1, denominator still can't equal 0. So add 1 to both sides. X can be anything to the left of 1 with everything to the right of 1. If you want to spend a little bit more time finding domains, I recommend checking out the video on 2.4. Okay, here, x minus 2, not allowed to be 0. X can't be 2. So x can be anything to the left of 2 with everything to the right of 2. All right, here we have two things. So x can't be negative 2 and it can't be 3. Set each one not equal to 0. So we can be everything to the left of negative 2, everything between negative 2 and 3, and everything to the right of 3. Okay, x squared minus 6x plus 8 can't be 0, right? Just keep taking the denominator, not equal to 0. Factor, set each factor not equal to 0. We can be everything to the left of 2, everything between 2 and 4, everything from 4 to infinity. Okay, well, same thing here. Set the denominator not equal to 0. Factor, set each factor equal to 0. We can be everything to the left of one of them, everything between them, everything to the right of them. And that's, it's going to be what happens for most of the time when it comes to two factors. If you have three factors, it works the same way. You would have left of the leftmost one, between them, and everything to the right of them. Oh, speaking of, let's do that right here. So we don't care about multiplicities here. We just care about what the zeros are. So x can't be 6, negative 54, positive 1/2 right here. Add 1 to both sides, divide by 2. So in order, we can be everything to the left of negative 54, everything between negative 54 and 1/2, everything between 1/2 and 6, and everything from 6 to infinity. So just be careful to write domain in order of how you would read x values from left to right. Okay, so basics domain, we've talked about that. But domain actually has an influence on this new thing called a vertical asymptote. So asymptotes in general are vertical or horizontal lines that your graph never crosses. So for example, in this rational function, we have two lines that are creating this weird behavior where we get really, really close to it, but we'll never hit it. Get really, really close to it, but never hit it. And same thing for the part up here. Now, the question is, when do they occur? And how do we know what the behavior is to each one? So some of the functions we were looking at before, x plus 1 over 4x minus 8, well, we weren't allowed to be equal to 2, so 2 was a vertical asymptote. X squared plus 2 over x plus 2x minus 3, x wasn't allowed to be equal to negative 2 or 3, so we get 2 asymptotes. Now, we might notice that there's slightly different behavior here, but That's just going to be the nature of rational functions, and we'll talk about that. So if you're finding the domain of a rational function, no matter what, always set the original denominator equal to 0. Domain of a function will never change. No matter how you can simplify, no matter what you can do to a function, there was one of the functions that we were just doing domains for that you could have simplified first. However, domain is always the original denominator, no matter what, period. However, to find vertical asymptotes, to find these vertical locations where things are weird, start by simplifying the function. After you do that, then you set the new denominator equal to 0. So you have some original function, no matter what it looks like. Don't try and cancel anything out. To find its domain, simply set the denominator equal to 0. But when we're going to look for vertical asymptotes, start by simplifying. So you already found the domain, now you simplify. Okay, so after you simplify, set the new denominator equal to 0. And now those locations that you get for x will result in vertical asymptotes, specifically vertical lines of the form x equals h. Now, what you might be wondering is, what about all the places that did cancel out? Well, right, setting the new denominator equal to 0 means that whatever corresponding values we get came from factors that didn't cancel out. Well, if a factor does cancel out, it results in what we call a hole. Now, here's the key part. Even though that factor canceled out, it still doesn't change that original domain that we found with the original denominator. We can't ignore where our simplified function came from. So we can simplify it. It could be easier to graph after we simplify, but we can't magically start plugging in values that we don't have. However, to graph a hole, all we need to do is plug in that x value that we canceled out. But we'll talk about that. So to graph rational functions, graph a simplified version of that graph. So for holes, what we're going to do is draw an open circle or a break in the graph. But then the question becomes is, how do we know which infinity each side of an asymptote it goes to? So we see that we're going to graph a simplified version. We see that we're going to graph holes when they're applicable, but that doesn't tell us anything about the asymptotes, right? The asymptotes themselves, it's just going to be a vertical line that we can put like a dotted line for. But when it goes to actually graphing it, how do we take into account that weird behavior to each side? So for asymptotes, we determine which infinity each side goes to by plugging in numbers really, really close to each side. So let's do the example 1 over x minus 3. Well, this is fully simplified, nothing else we need to do. And when we set this new denominator equal to 0, we get a vertical asymptote at x equals 3. So to take care of a vertical asymptote at x equals 3, we need to figure out what's the behavior as we get closer to 3 from the left. Are we going up as we approach 3 or down as we approach 3? And likewise, when we approach 3 from the right, are we going up or are we going down? So what we're going to do is plug in numbers really, really, really close to 3. So for example, you would plug in something like 2.999 for the left and 3.001 for the right. Now, here's something to keep in mind. We don't actually care what the value is when we plug these numbers in. We already know that the behavior is either going to infinity or negative infinity from each side. So all we care to figure out is the sign of infinity. So for example, when we plug in 2.999, well, 1 over 2.999 minus 3 is 1 over negative 0.001, and this is a positive number divided by a negative number. Positive divided by a negative is a negative number. So in this case, to the left of x equals 3, we are approaching negative infinity. Again, did not care at all what the value was. All we care about is the sign of infinity. For 3.001, okay, well, 3.001 minus 3 is positive 0.001, and this is a positive number, so 1 divided by a positive number will be positive infinity. So from the left of 3, we're going to go down to negative infinity, but from the right of 3, we're going to go up to positive infinity. So there we go. As we approach 3 from the left, as we approach 3 from the right, negative and positive respectively, just like we found. Now, this weird behavior that's happening down here, we'll come back to that. Okay, let's do the same thing, but for 1 over x minus 1. Well, we have a vertical asymptote at where this denominator is equal to 0 and x equals 1. So we're going to plug in numbers very, very close to 1 from the left and from the right. So let's plug in 0.999 for the left and 1.001 for the right. When we plug in 0.999, we get 1 over negative 0.001, which is negative. So 1 divided by a negative number is a negative. 1.001, well, 1.001 minus 1 is 0.001, which is positive. 1 divided by a positive number is a positive infinity. So we're going to graph a vertical asymptote at x equals 1. Left side is going to go down. Right side is going to go up. Okay. Let's do this again, but now we have two things, right? X squared minus 9 is x plus 3x minus 3. So we're going to do a vertical asymptote at negative 3 and at 3. We have two vertical asymptotes, and that's totally okay. So, however, because we have two vertical asymptotes, we need to check the behavior from each side for both of them. So let's start with x equals negative 3. For the left, we're going to plug in negative 3.001. And for the right, we're going to plug in negative 2.999. So just be very careful, right? Negative, normally we would associate the 0.999 from the left when it comes to positive, but when we're negative, negative 3.001 is to the left of negative 3. Okay, so let's plug it into this factored version. Negative 3.001 plus 3, negative 3.001 minus 3. And I again want to remind you, we don't care about the value, we only care about the signs. So forget about trying to calculate this thing. Here, negative 3.001 plus 3 is just negative, and negative 3.001 minus 3 is also negative. So 1 divided by a negative times a negative, well, negative times a negative is a positive. So in total, positive infinity. Okay. Let's do the same thing for negative 2.999 plus, or negative 2.999 from the right. So this will be positive. This will be negative. Positive times a negative is a negative. So in total, we get negative infinity. So for this specific vertical asymptote, x equals negative 3, we're going to go up from the left and down from the right. Okay, well, we got to repeat the same process for the second vertical asymptote. So let's do 2.999 for the left and 3.001 for the right. 2.999. All right. This one, positive. This one, negative. Positive times a negative is a negative. Whole thing, negative infinity. 3.001. Okay, this is positive. This is positive. Positive times a positive is a positive. So in total, we get positive infinity. So for this vertical asymptote, we're going down and then up from each side. So in total, we went to positive infinity, negative infinity, negative infinity, positive infinity. So positive, negative, negative, and positive. Who chose the specific window so that's so hard to tell? I don't know. It might be somebody on the screen's fault, but I think we get the idea. Okay, well, let's graph with some holes now. So holes occur at the locations where factors cancel out. So let's start by simplifying. So simplify first. If a factor does not cancel out, it's a vertical asymptote. But if a factor does cancel out, it is a hole. All right, so x squared minus 9 is x plus 3x minus 3. and we can cancel out x minus 3. Okay, so what we're going to do is graph simplified version of the graph. This is the simplified version, but we're going to draw a hole where this factor canceled out. So this corresponding x value is x equals 3. And since there's no more denominator, it's actually pretty nice. So there's no more vertical asymptotes. So in total, we're just going to graph x plus 3 and put a hole at x equals 3. And that's the extent of drawing some rational functions, right? We're still very low, but nonetheless, this is how this works. Okay, let's do the same thing, but flipped and see how this would work. Well, we're going to simplify first. And same thing, if a factor doesn't cancel out, vertical asymptote. If a factor does cancel out, hole. Okay, well, x plus 3, x minus 3, and x minus 3 cancels out. So we're going to graph this simplified version, but x equals 3, once again, canceled out, right? I know x minus 3, the factor canceled out, but the corresponding x value to x minus 3 is x equals positive 3. So there's a vertical asymptote at this location that did not cancel out at x equals negative 3. From the left of negative 3, the graph goes down. From the right of negative 3, the graph goes up. You could check this doing that 2.999 and 3.001 stuff we did before, but here we go. Negative and positive, and there is our hole for this function. Okay, let's do another one. X plus 2 over x squared minus 2x minus 8. So let's simplify first. If a factor doesn't cancel out, it's a vertical asymptote. If a factor does cancel out, it's a hole. So x squared minus 2x minus 8, x minus 4 times x plus 2. X plus 2 cancels out. So we're going to graph 1 over x minus. This should be 1 over x minus 4. I don't know how that happens. So we're going to graph 1 over x minus 4, like it's right here, but we're going to graph a hole at x equals negative 2. So there's a vertical asymptote at x equals positive 4, right? Again, this should be minus. So when you go to x equals 4 from the left, you go to negative infinity. When you go to x equals 4 from the right, you go to positive infinity. And there we go. All right, some more graphs with holes. Here we go, 3 minus x over x squared minus 6x plus 9. All right, let's simplify first. Okay, denominator factors to x minus 3 squared, and this is pretty close. So what if we factored out a negative 1 from the top? Okay, well, x minus 3, well, one of them cancels out. So we're going to graph this simplified version. However, there's a vertical asymptote at the location that did not cancel out. So there's a vertical asymptote at x equals 3. So from the left of 3, we go to positive infinity. A little backwards from before since we have this negative sign up here. And from the right of 3, we're going to go to negative infinity. Now you might be wondering, why isn't x equals 3 a whole, right? X minus 3 canceled out. Well, it didn't perfectly cancel out. It didn't cancel it out everywhere. It's still remaining in the denominator. So its status as a vertical asymptote has to supersede that of a hole, right? You can't have a vertical asymptote in a hole. That doesn't make any sense. So in this case, its graph would look identical to negative 1 over, was it x plus 3? No, negative 1 over x minus 3. Okay. Well, that's vertical asymptotes. That's holes a little bit. So now let's talk about horizontal asymptotes. Now you're probably thinking, oh my God, we keep getting closer and closer to the end, and the stuff keeps getting harder and harder. Don't worry, it's actually not that bad. If anything, it's even better. So vertical asymptotes are vertical lines that your graph never crosses. But horizontal asymptotes are kind of funny. Horizontal asymptotes are horizontal lines that your graph sometimes can cross. So we can't necessarily explain it right now. Horizontal asymptotes essentially are tied to the end behavior of rational functions. We talked about end behavior for polynomials, but we can't really talk about end behavior for rational functions. It's a little quirkier than that. And if anything, it actually requires Calculus 1 to come up with, including all of these below rules to help us find horizontal asymptotes. So what we're going to do is compare the degrees of the numerator and denominator, right? Rational function, numerator and denominator, compare the degree of the numerator with the degree of the denominator. In this case, when the degree of the numerator is less than the degree of the denominator. So for example, something like x squared divided by x cubed, well, you would have a horizontal asymptote at y equals 0, or also just the x-axis. If the degrees are equal, then there's a horizontal asymptote at the quotient of the leading terms. Okay, that one's kind of weird. We'll come back to that one. However, if the degree of the numerator is bigger, there is no horizontal asymptote. So it's either going to be y equals 0 at the quotient of leading terms or no horizontal asymptote. Okay, so let's just do 2 slides entirely finding horizontal asymptotes. Okay, in this case, the numerator is 1, denominator is x minus 3. The degree of the denominator is 1 for x to the 1. Well, since there's no x in the numerator, this is degree 0. So numerator is 0, denominator is degree 1. So the degree of the numerator is less than the degree of the denominator. And now just pull the rule from the last slide. When the numerator is less than the denominator in terms of degrees, there is a horizontal asymptote at y equals 0. Okay. Here we have 3x squared minus 1 over x plus 2. The degree of the numerator is 2. Degree of the denominator is 1, right? X to the 1. Well, in this case, the degree of the numerator is bigger than the degree of the denominator, 2 over 1. Okay, when the degree of the numerator is bigger, there is no horizontal asymptote. Okay. Find the horizontal asymptote of x plus 1 over 4x minus 8. Okay, well here, x is degree 1, 4x is also degree 1, so the numerator and denominator are both degree 1. They're both equal. So here's what we're going to do. We're going to take those leading terms and divide them. So there will be a horizontal asymptote at y equals x over 4x. Well, cancel out an x, and we get 1/4. So there is a horizontal asymptote at y equals 1/4. All right, horizontal asymptote of 2x over x squared plus 1. Degree of the numerator is 1 for 2x to the 1. Degree of the denominator is x squared, degree 2. So the numerator is 1, denominator is 2. The degree of the numerator is less than the degree of the denominator. So we have a horizontal asymptote at y equals 0. Right? We're just pulling rules from the last slide. Here, 3x cubed plus 2x squared plus x over 2x plus 5. The degree of the numerator is 3. Degree of the denominator is 1. Numerator is bigger. The rule for bigger numerator is no horizontal asymptote. Okay, so let's do another slide of these. Horizontal asymptote of 5x plus 2 over negative 3x plus 1. Degree of the numerator is 1. Degree of the denominator is also 1. So we're going to take those leading terms and divide them. Cancel out the x, and we get negative 5/3. Okay, horizontal asymptote of x cubed plus 1 over 4x to the 4th plus 1. The degree of the numerator is 3. Degree of the denominator is 4. So degree of the numerator is less than the degree of the denominator. So in the case where it is less than, there is a horizontal asymptote at y equals 0. All right, x squared plus 2 over x plus 2x minus 3. Well, let's FOIL out the denominator. And now you see degree 2 in the numerator, degree 2 in the denominator. So take those leading terms and divide them. X squared divided by x squared is just 1. 4x to the 4th plus 1 over x cubed plus 1. Degree of the numerator is 4. Degree of the denominator is 3. So numerator is bigger, there is no horizontal asymptote. All right, one more example. Here, the degree of the numerator is 2, degree of the denominator also 2. So take those degree 2 terms and divide them, and we get negative 3/4. So horizontal asymptotes, even easier to find. Okay, and now let's put all of this together to graph rational functions. This is how we're going to sunset algebra in chapter 3. So here we go. So to graph a rational function, start by finding the domain. You don't necessarily need it to graph. However, it is a very important part of the function, and it helps remind us that we can't magically start plugging in values. It reminds us that we need vertical asymptotes and we need holes. So set the original denominator equal to 0. Then simplify the function. If a factor cancels out, it's a hole. But if a factor doesn't cancel out, it's a vertical asymptote. And then check numbers to the left and right of that vertical asymptote to determine which side, to determine which infinity each side goes to. And we like to sketch vertical asymptotes as dotted lines. To find horizontal asymptote, we're going to sketch that as a dotted line, but just use the 3 rules that we just talked about. Okay, find zeros and x-intercepts, set the numerator equal to 0, and last but not least, find the y-intercept by setting x equal to 0, right? Come full circle to x and y-intercepts that we've been doing since very early in chapter 2. And we sketch based on all of this information. Okay, let's graph 1 over x plus 5. So domain, we want to make sure that the denominator doesn't equal 0. Subtract 5 on both sides, so we can be everything except -5, which is everything to the left of -5 with everything to the right of -5. Okay, simplify the function. Well, in this case, there's nothing to simplify. So that means we have a vertical asymptote at the factor that didn't cancel out, which is x equals -5. So to the left of -5, we're going to go to negative infinity. To the right of -5, we're going to go to positive infinity. And there's no holes since we didn't have any factors to cancel out. Horizontal asymptote, let's compare the degree of the numerator and degree of the denominator. Degree of the numerator is x to the 0, so just 0. Degree of the denominator is 1, x to the 1. So the numerator is less than the denominator in terms of degree. When the numerator is less than, there's a horizontal asymptote at y equals 0. X-intercepts, we set the numerator equal to 0. However, obviously 1 is never going to equal 0, so there's no x-intercepts. That's totally fine. Y-intercept, we're going to set x equal to 0. So 1 over 0 plus 5, 1/5. Okay, all that said together, all that put together, all that said and done, right? We've come a long way. There we go. All righty. Another one, 6 over x squared minus 1. Let's start with the domain. Need to make sure the denominator doesn't equal 0. Well, x squared minus 1 is x plus 1, x minus 1. Set each one equal to 0. And we get everything to the left of -1 with everything to the right of -1. Sorry. And we get everything to the left of -1, everything between -1 and 1, and everything to the right of 1. Simplify the function. Well, nothing we need to do here. So that means we have vertical asymptotes at both values that did not cancel out. To the left of -1, we're going to go to positive infinity. To the right of -1, we're going to go to negative infinity. To the left of positive 1, we're going to go to negative infinity. And to the right of 1, we're going to go to positive infinity. So again, I did the practice of checking both left and right hand side when we initially talked about vertical asymptotes. So if you need help with that, scroll back a little bit in the presentation. And there's no holes because nothing canceled out. Horizontal asymptote, all right, numerator is degree 0, denominator is degree 2. So the numerator is less than the denominator, and we have a horizontal asymptote at y equals 0. X-intercepts, set the numerator equal to 0, but 6 doesn't equal 0, so we're good there. Y-intercept, set x equal to 0, so 6 over 0 squared minus 1. 0 squared is 0. 0 minus 1 is negative 1, or negative 6, or 0, negative 6 is our y-intercept. And there we go. Okay, 1 over x minus 2 squared. Domain, set the original denominator equal to 0, or not equal to 0. Square root both sides, add 2 to both sides, and we get everything to the left of 2 with everything to the right of 2. All right, let's simplify. And we don't have any simplification to do here either. Vertical asymptote's going to be at x equals 2. And now, interesting quirk here. Notice that no matter what you plug into this function, so you take any number you want, you subtract 2, whatever it is, the second that you square it, it's going to be positive. So no matter what, we will always get a positive value for each of these, including both sides that the function approaches for the vertical asymptote. And again, nothing canceled out, so no holes. The degree of the numerator is 0, degree of the denominator is 2, so numerator is less than, we have a horizontal asymptote at y equals 0. X-intercepts, none, since the numerator still doesn't equal 0. I promise we'll look at least one example where this is different. And then y-intercept, set x equal to 0. 0 minus 2 is negative 2. Negative 2 squared is positive 4. So 0, 1/4. And there we go. Okay, some more exciting stuff is going to happen in this one. All right, domain first, set the denominator equal to 0. Subtract 2, divide by 2, and we get everything to the left of negative 1 with everything to the right of negative 1. Let's simplify. Well, in this case, also nothing to simplify. So we have a vertical asymptote at that x equals negative 1 that didn't cancel out. And here, just be very careful, right? In a lot of the other cases that we've had to deal with, when we plug in numbers to the left and to the right of the vertical asymptote, we normally only had to plug things into the denominator, but be careful because now you need to plug in that value into every x that you see, not just the denominator. So doing so, to the left of negative 1, you'll get positive infinity, and to the right of negative 1, you will get negative infinity. Still nothing canceled out, so still no holes. Okay, degree of the numerator is x to the 1, 1. Denominator is 2x to the 1. So for the first time, the degrees are equal. So there's a horizontal asymptote at y equals x over 2x. Take those leading terms and divide them. Cancel out an x, we get 1/2. So we have a horizontal asymptote at y equals 1/2. X-intercepts. X-intercepts say to set the numerator equal to 0. Oh, finally we can do that. Add 3 to both sides, and we get 3, 0. Y-intercept, set x equal to 0. So we get negative 3 at the top, 2 at the bottom. So 0, negative 3 over 2. All right. And 2 more examples, and then we sunset college algebra. All right, so I give you this very beautiful looking function here. I'll just give you the factored version here, don't worry. So step 1, find the domain, set the denominator equal to 0. So we get negative 3/4 and 5/3. So that is everything to the left of negative 3/4, everything between negative 3/4 and 5/3, and everything to the right of 5/3. Simplifying the function, well, notice 4x plus 3 goes away, 3x minus 5 goes away, so we get 4x minus 9, and this is going to be a lot easier to deal with than some of the other stuff we've had to work with. Vertical asymptote, there's none. There's no more denominator. Nice. But we do have holes at those 2 x values that we canceled out, so we got to keep going. Horizontal asymptote, the degree of the numerator is bigger than the degree of the denominator since there's no more denominator, so there's no horizontal asymptote. And we knew that this is a line, so lines don't have horizontal asymptotes. X-intercepts, set the whole thing equal to 0, add 9, divide by 4, we get 9/4 comma 0, and y-intercept, set x equal to 0, well, we just get 0 comma -9. So kind of an interesting looking function when we do that. Okay. One more example. Let's just flip the numerator and denominator, and then we'll call it a day. Domain, set the denominator equal to 0. Oh, well, this time we actually get 3 values that this happens. So in order, we can be everything to the left of -3/4, everything between -3/4 and 5/3, everything between 5/3 and 9/4, and everything to the right of 9/4. Now let's simplify. You'll see the same two factors cancel out, except now we have 4x minus 9 in the denominator. So some of the rules that we just had, or some of the things we just talked about, are going to be a little opposite. So there's a vertical asymptote at this remaining term, right? 4x minus 9 didn't cancel out. So we have a vertical asymptote at 9/4. To the left of 9/4, it's going to be negative infinity. To the right of 9/4, it's going to be positive infinity. And we have holes at those two values that canceled out. Well, this time, the degree of the numerator is 0. The degree of the denominator is 1. So numerator is less than again, horizontal asymptote at y equals 0. X-intercepts set the numerator equal to 0. That never happens. So we have y-intercept when x is equal to 0. So we get -1/9. Very nice. And there is our graph. And that is the end of my college algebra lectures. So that's it. I like, 3.4 and 5 being the end, but sometimes we don't always have it our way. So with that said, thank you so much for watching 3.6. And if you've watched other videos, thank you so much for watching all the lectures here in college algebra. And I hope these videos have helped. So bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.